Okay,
So Jerison's second talk today is on the geometry of level sets.
We're all good.
thank you very much. Thank you, everybody, for. Thanks a lot, everybody. We're having a few technical difficulties today, but we're okay. And my pointer works too, so we're good. All right, this is talk number 2, geometry of level sets. We're going to pick up where we left off last time, and I'll remind you where we were. All right, we're hoping to do some differential geometry today. So let me remind you what I talked about in the last lecture. I said that if you take a semilinear elliptic equation, Laplacian of u is equal to f of u, and the function is not in the neighborhood of a point which is not a critical point, so the gradient doesn't vanish, and there's a sign condition which just has to do with directionality of where the flow is going. And so we define the normal vector, as this the gradient divided by its length. Okay, so we're going in the direction of positive increase of u. That's a choice. That's just a conventional choice. And then we're going to flow in that direction by the reciprocal of the gradient. And that will move us in time t between, and maybe I should have put a reciprocal tau here because that's the label that I used of the level set u. That will move us along level sets of u. All right, so that's the situation that and that's the way we're interpreting level sets, as we're interpreting as a kind of a flow. And the claim was last time, at the end of last time, was that this process decreases flux, the gradient of u times the surface area, fastest, in completely analogously to the way that mean curvature flow decreases surface area. And so the suggestion, and I drew some pictures of it last time, is that this means that we should look for formulas in the spirit of the ones that Richard Hamilton used when he studied mean curvature flow and Ricci flow. And in particular, we really like the idea maybe of finding some of these pinching theorems, which say that things are going to get rounder and more rigid as we go towards the ellipsoid, and for the Harnack inequalities that the gradient is bounded away from zero in some quantitative sense. So to get started, I'm going to just in one slide tell you, roughly speaking, what types of formulas Hamilton uses. Okay? So he basically starts with the metric, which is the first fundamental form of the surface, and he differentiates it with respect to time. And then actually he differentiates these tensors many, many, many times. All right? It just keeps on going. So the Hij is the notation for the so-called second fundamental form. And then you can also take the Laplace-Beltrami of that. That's not the Laplacian, that's the Laplace-Beltrami on the surface, and so on. But you can differentiate with respect to these things and just keep on going and going and going with higher and higher tensors, which are both extrinsic and intrinsic tensors. Now, it's a little easier for me to describe what the formulas look like by switching to the context of Ricci flow. Even though, of course, I'm not going to tell you the forms, I'm just telling you superficially what their form looks like. They're quite complicated, okay? Richard Hamilton is actually the person who introduced Ricci flow, in addition to proving the most important theorems about it up to the point when Perelman took over and put things over the finish line. So he's Moses in this story, and Grisha Perelman, who finished the geometrization conjecture, is Joshua. He got to the promised land. All right? So the first thing that Hamilton introduced is the Ricci flow itself, which is the evolution so you have a compact Riemannian manifold that has a metric, which I'm calling Gij. I'll say a few things about geometry later, but you should just imagine you have a tensor, you have a matrix on a manifold, and you're flowing it in some direction. And the rate at which you're doing it this is a system of equations, is proportional to the Ricci tensor, which is another symmetric 2 tensor on this manifold, and it's the natural one. It turns out that this is an unbelievably natural equation. So that's the formula. And in terms of differential equations, if you think of the unknowns as being the GIJs, this matrix of stuff, the R here, the Ricci tensor, is built out of second derivatives. So this is like a parabolic equation, and it's a second, it's an ordinary, it's a parabolic equation. Because it has diffeomorphisms acting on it, it's got some complicated degeneracy that took a long time to work out. But that was done in the 1980s. From 1982 to 1993, Hamilton worked on this problem really a lot, and he differentiated the equation more and more and more and found more and more amazing structure. So when he differentiated the metric 4 times, he got an equation which was unbelievably beautiful. It's a semi-linear equation now. It's the whole Riemann curvature tensor of this thing, which depends on 2 derivatives of G, is then differentiated 2 more times. And you get an expression which is only in terms of the Riemann curvature tensor itself. So in the terminology of maybe general relativity or various other geometric equations, this system of equations closes at this point. It's self-referential, as opposed to being in terms of other stuff that you don't understand as well. So this is an extremely useful type of formula. And there's a lot to do to understand how to use it, but basically this allowed him to show that if you start with a positive Ricci manifold, a manifold in which this tensor here is positive definite, then it converges to a sphere and shrinks to a point. That's the pinching, is that the curvatures are all balanced and it gets more and more like a sphere, and then it vanishes when it contracts to a point. So that's the first type of theorem that he proved. The second type of theorem, it has to do with Harnack inequalities, which have to do with various scalar quantities and eigenvalues of various matrices being comparable at different parts of space-time. And that's a much more complicated thing. That involves 6 derivatives of the metric. And what you do is you take this Ricci, and then you take its Laplacian, and then you contract it with some vector fields, and then you take the heat operator on that. So that's the total, right? So R is 2 derivatives of G, and then you're taking another 2, and then you're taking another 2. All right? So it's some fancy, amazing formula which has an amazing pattern here. And
these vector fields arbitrary, or do they?
Oh, that's a very good question. So the question, I stuck in these vector fields. It turns out that there's a differential inequality that's satisfied for arbitrary vector fields, but the way you prove it is by flowing them in a particular way. This is an extremely sophisticated subject, and you're flowing them by space-time, but then eventually you get a conclusion at single point for arbitrary vector fields. And the reason for that is essentially a parabolic maximum principle. But I cannot possibly tell you the whole history of this subject. But that was a very good question. And you just uncovered little pieces that I'm skipping here, all right? Of which there are many, many more. I apologize, but this has to be very compressed. Now, it turns out that there's actually an analogy between this equation and that equation. This turns out to be in disguise some contraction of some curvature of some fancier bundle sitting on top of this, so that this identity and this identity are actually related in some heuristic sense. And that was worked out later by Chow and Chu, and used tremendously by Perelman.
It's the M sub I, J, K, L. What does that depend on? Is that on?
Well, the Riemann curvature tensor is a 4 tensor, and so it has 4 indices.
Oh, I didn't realize that.
And they are contracting it against the Laplacian of the Ricci, which has 2 indices, and then you have these other 2, this vector field.
RM stands for the Riemann tensor.
Yeah, RM, sorry, I didn't explain that. I had that on another slide, and I managed to blip it off of this slide. I'm sorry. Yeah, so this is a this is a crash course. There's going to be more crash course, which is a little more elementary stuff that I'll do in a second with Riemannian geometry. I apologize for I can see that this is going to take a while, and maybe we'll only get halfway through this particular lecture, which we will live with, all right? Maybe this will be all I can explain in this lecture and the next. We'll see. Okay, anyway, so the goal is we sort of want to do something like this. And we know that we're stuck with maybe taking as many as 6 derivatives at some point, which means that there's no chance that we can do this without having some idea what we're doing. We'll get completely lost in the formulas, as actually I did for years and years, wandering in the, so I think of it as skiing around in the jet bundle. When you have a harmonic function, its Taylor series can be thought of invariantly as being in a certain bundle, which is called the jet bundle. It's just every Taylor series can be thought of. If you track it under changes of variables, it's in something called the jet bundle. And I hate jet bundles, and you should too. Analysts, it's just too complicated. You just get lost after a certain number of derivatives. So you have to have some guidance. You have to know what you're looking for. And I'm going to be able to explain to you that I think I know what's the right way to guide this thing, but it's hard. Okay, it's not.
What is the purpose of all this to get the pinching theorem?
Yeah. So you take this identity and then you contract this in certain ways. So this is a 4/10. You contract it in certain ways, and you get and then you get a scalar quantity, various scalar quantities, and then you have a maximum principle, a parabolic maximum principle, and that parabolic maximum principle is telling you that for example, the simplest thing it's telling you is that if the Ricci starts out positive, it stays positive as a symmetric matrix.
So the equation with R set M, the fourth derivative, this is used for this pinching theorem.
Exactly. To obtain pinching, he computes this identity, and then and the one with 6 derivatives you need for the Harnack inequalities.
So there's something else.
Yeah, that's right. There are 2 types of theorems. There are theorems which say that curvature gets more and more similar, so it resembles more and more of a sphere. And then the other ones are saying that, say, scalar curvature and various other contractions, but in particular, scalar curvature at one point and scalar curvature at another point are comparable somehow in the same way that they would be for a parabolic equation.
The Harnack inequality for systems.
The Harnack inequality ends up being eventually being for scalar quantities, but they're contractions of much more complicated tensor quantities. So each time you're making a scalar greater than 0 statement. But I'll actually talk about in the 3rd lecture when I get there. I'll tell you what some of these Harnack inequalities look like. All right, exactly what they look like. And essentially, the directional derivative of the log of something has a sign, has some control to it. Okay. Okay, all right. Well, so anyway, I'm sorry. We're just looking for some formulas. They have to have some connection with the geometry of level surfaces. Now, the other thing to recognize, so let's keep on going here. All right, so Hamilton discovered these amazing formulas by looking at solitons. And the simplest example of a soliton, and this is true both for mean curvature flow and for Ricci flow, is just contracting spheres, which shrink to a point. So that's a self-similar solution to the equation, it turns out, right? That's, and more generally, you think of the Ricci tensor as being just a multiple of the metric, and then all you'll be doing is you're changing the scale of the metric. Everything is just the identity on that. And those are called shrinkers. There also are expanders. You could go the other way, or steady solutions. And the way that you look for them is the inequalities that you want turn out to be on the nose. They're just identically equal for the solitons. And so that's how you can guess what the formulas look like. So you have to really understand what the solitons are, and you have to be able to compute with them. And in some cases, they're explicit, but like in 2 dimensions, but they become not even explicit. You just have identities for them in some cases, so it's not so easy. Now, our solitons are just going to be harmonic functions. It turns out that you don't have to solve the most general situation. I have Laplacian u is equal to f of u, but if you had just set that equal to 0, you can put back in by hand the formulas that will account for the right-hand side. The right-hand side is not the complication. All of the complexity is already present when you have harmonic functions. So you do not have to, thank goodness, you don't have to worry about whatever the heck is going on. It's just one less thing to pay attention to. All right? So we're just talking about the equation now, Laplacian u is equal to 0, and that's going to give us our whole framework. Okay? And the solitons, so I'm telling you that the right solitons to look at have to have something to do with ellipsoids. Because remember last time, what happens when you shrink to a point, those are the sort of the steady, those are the solitons. They looked like ellipsoids when we shrank to a point. That was what we were doing yesterday with eigenfunctions. They shrank to an ellipsoid. Now, the ellipsoid was sort of cut off at the end when it was the Neumann problem, but that's just because the domain sliced it off. It was still an ellipsoid centered at that point. They were just quadratics, okay? And as every function is near a point, right? Every smooth function. Now, amazingly, the right family is what are called confocal ellipsoids, and I'll explain in great detail what confocal ellipsoids are, and we're just going to meet this structure, which was classical and started with Newton, okay? Newton is the first person who cared about these, and that's because he thought that the Earth was an ellipsoid. It's true, actually. It's not quite spherical. It's a little distorted, and it's the best approximation, modulo mountains or something like that, is that it's an ellipsoid. And he was very worried about that because he wanted to be able to treat it like a point when he was doing the orbits of the planets. And this may have been the very thing that delayed his publication by 20 years. But he did figure out what he needed to know. So he started this subject. And Ivory discovered much more detail about the level sets of the potential, of the gravitational potential in the vicinity of the ellipsoid. And then this was elaborated on by Jacobi, whose work we're going to be talking about in great detail. This is essentially the first time when the coordinates that we're going to be studying were discovered in the 3D case. And many, many other people have studied this intensely. It was of great interest in the 19th century, tremendously. And even in the 1950s, in the next century, Pauly and Sego have a beautiful conjecture, which I'll mention later, which is directly connected to this family of examples. So this is a beautiful set of examples that everybody should learn about. And so I'm going to tell you about them today. If you missed them, if you didn't read certain old texts. It's in Whittaker and Watson from the 1920s. And there are a bunch of books that have talked about this for many years. Okay, so we'll meet those. So these are our harmonic functions, and we'll look at them on the next, I'll just tell you what they are on the next slide, but it'll take us a while to get used to them. So here they are. It turns out that there's this huge family of them, and they're, what's happening is that they're families of quadratic surfaces. And these are the level sets of these very natural harmonic functions. So basically you get every ellipsoid, and you get every hyperboloid, and you get every signature of every, every quadratic. And then there are natural harmonic functions which have those as level sets. But they're not, you don't get concentric ellipsoids, you get what are called confocal ellipsoids. In other words, they're not dilates of each other, they're something else. And the formula is just sitting right here. So this formula is a formula for a surface if you fix S. And I'm calling it E for ellipsoid. And of course, if S is big enough, if S is bigger than minus AN, then this will be an ellipsoid. Okay? On the other hand, if you move S so that it crosses over so that one of these denominators switches sign, you're changing the signature. All right? And so you're getting a quadric surface of a different type, you know, pluses and then one minus. All right? And then if you cross another one of these values, you're getting the next signature, and so on, and so on, and so on. And this family, as I say, was studied all the way through the 1800s in great detail, and it's of central importance in many subjects, okay? Some of which have vanished, but definitely not all of them, okay? And I'll mention a few of them as we go along. Anyway, so now, how do you get a harmonic function whose level surfaces are these sets? Well, the answer is it has to be a function of that variable S, all right? That's all you need. So you need to figure out, so it turns out that in fact, if it solves this ODE here, it'll be a harmonic function, okay? So that means that what you need to do in order to express these harmonic functions, you need to integrate this function here. That's a famous integral. When you're in 2D, you just only have a1 squared and a2 squared and none of the rest of these. This is an explicit function, which we'll be writing down. It's expressed in terms of sines and cosines. When you have 3 factors, these are very famous. They're called elliptic integrals. And when there are more factors, they're called hyperelliptic integrals. And as I say, they were studied all through the 1800s. All right? So these are some special functions which are very interesting, which we'll be discussing and which are directly relevant to what we've got. Now, so you have this function which has this derivative, and I don't care what the constant is because that doesn't change the level surfaces, the constant of integration. But I am going to distinguish between when the parameter is bigger than the top one, so we're just getting ellipsoids. That's the top one. That's mu sub n, which is in the range all the way. So S is starting at minus an squared and going all the way to plus infinity. Those are the ellipsoids. And then the next signature and the next and the next and the next. And that gives me a whole bunch of harmonic functions. Now, what's beautiful about these is they form an orthogonal system, okay? They're perpendicular to each other. This is a great coordinate system. This is a coordinate system in which you can separate out and solve the Helmholtz equation, the wave equation. There are tons of special functions. Even engineers are using this now as we speak to solve various problems with explicit special functions. So this was used for separation of variables in the 1800s and is still used. So I'm going to draw some pictures of these things. But first I want to mention, so here we were supposed to turn on these lights, but we forgot. Bummer. Yeah, right. We had so much trouble with the audio that, right? Okay, so there's a famous problem, which is the isoparametric problem for capacity. Which was introduced by Polya and Sego. And I can see that people are going to have trouble here, so I'm going to put it over on this part of the blackboard, if that's better for people. So the idea is the following: Newton didn't know about anything but gravitation, but that's beautiful. Thank you. Do you need more? Oh, maybe over there. So, but now the light is on the. Oh well, doesn't matter. It's okay. Did that work? Oh. Yeah, so we're going to eventually have to turn it off so that we can see the screen. Okay, look. So if you take a, boy, this is taking me about 5 times as long as I had hoped, but we'll live with it. If you take a conductor, so we're switching from gravitational potential to voltage, to electrical potential. And if you have a conductor, okay, which happens to be a convex piece of metal, then if you put some electrons on it, they will all go to the boundary, and they'll induce a an electrical field. And the electrical field will be 0 inside because that's what the equilibrium is, because it's a conductor. And then outside, there will be level lines of voltage, okay? That is, the energy levels will be descending to 0, all right? So that's what it says on the slide. It says you have a function, and I'm just fixing the, just by fiat, 1 volt on the boundary. And then as you go to infinity, the voltage is dropping to 0, okay? There's a technicality in 2D. There's a logarithmic pole at infinity, so you have a slightly different formula, so it's necessary to just take the case n greater than or equal to 3 just so that I don't have to write extra stuff here. Now, by definition, the capacity is the factor on the Newtonian potential that you get. That is, think of this as being a point mass at infinity. It's how much it would be like. It's going to resemble the fundamental solution at infinity and so which multiple you get is some notion of how big omega is, and it also happens to be exactly equal up to some dimensional constant to the if you like, the number of electrons on the conductor. So that's its capacity, okay? It's also the same as the total energy, the Dirichlet energy of the whole configuration. So there are lots of equivalent ways of defining the capacity, but one of them is it's the asymptotic of U as you viewed from infinity. All right, so that's called capacity of this metal body. And then Poya and Sego introduced this isoparametric problem for capacity. And what it says is the following. You're taking so capacity is naturally of dimension n minus 2. It's logarithmic in dimension 2, and when n is equal to 3, which is it's of dimension 1. All right, it scales like dimension 1 when you okay. Surface area scales like dimension 2 when n is equal to 3. As we know, surface area is 2-dimensional. And so this ratio is balanced in homogeneity. Now, this is completely analogous to an ordinary isoparametric inequality where you have a sort of a difference in homogeneity and you take a ratio and the sort of more singular thing you put upstairs and the less singular thing you put downstairs. And you take the ratio and you see what happens. And the minimizer for this thing, the surprise is that it's not the ball. So this is a very cool problem because it's a symmetry breaking problem where the answer is not the ball. And what Poya and Sego did is they showed that, in fact, they gave the obvious candidate, which turns out to be what happens is you take an ellipsoid, which actually has rotational symmetry in one direction, and then you go all the way down until it collapses. And when it collapses on a flat disk. And that's the guy. That's the one. So it's, if you like, it's not achieved by an open convex set. It's a limiting thing. But anyway, that's the extremal for this problem. That's the conjecture. And what they showed is that for all of the ellipsoids, every single one of them, including, of course, the sphere, the most interesting one, are unstable. They're definitely not. So none of them could possibly be the extremal. And they suspected that it was this collapsed disk. And then they also showed that if it's a two-dimensional body, then the disk is correct. So that was already in 1950. And by now, there are much, much stronger theorems that say that basically anything that's positively curved or anything that's a polyhedron, none of those things can possibly be the correct answer. But unfortunately, there's some subtle regularity questions that prevent us. This theorem is close to being proved, but it's not. Okay. Anyway, I'm hoping what I'm doing will help with that, but since I'm not claiming to prove any theorems, I'm not going to make any claims. Okay, but this is another question. So this thing that I just drew is just another family of nice, it turns out that the level sets are always convex in this context. And this is another beautiful kind of question like the one that I did last time with the Dirichlet ground state eigenfunction. Except instead of things going in towards an ellipsoid at the limit, they go out towards something which is a big sphere at infinity. It's getting rounder and rounder as you go to infinity. But anyway, it's just another one of these level set evolution questions. And again, it's unsolved, so it's interesting. All right. Okay, so now I'm going to draw you the picture of what they are in 2D. In 2 dimensions, it's a little simpler. You have the foci, and you have the segment between them, if you like. All right? Or maybe I should draw it over here. It looks like I'm having a little trouble with. So here we are. These are the foci of the ellipses. And then you have the little ones, which are rounded. They collapse to this flat thing. Okay? And then you have a somewhat bigger one. All right? And then they get bigger, and it's like this other picture. At infinity, they get rounder and rounder and rounder. All right? But it's because viewed from infinity, these foci are as if they were at a single point. So obviously, the limiting thing is the circle, right? As you get larger. Now, that's one family of level surfaces. The other ones are the hyperbolas, which are the orthogonal family that goes the other way. I'm sorry, my picture is pretty lousy, but that's what the other quadrics look like. Okay? And what these are is they're the images. If you look at the map, z goes to a complex number times the hyperbolic cosine of another complex number times z, well, up to rotations and so on, where these are just fixed complex numbers. And z is, if you take some parallel lines in here, and you take their image, they'll be one of these families of things. Yeah, question. Yeah, they're the level sets of functions that are harmonic conjugates. So they're the arc hyperbolic cosine function. They're the inverse functions of this. This is the parametrization, and they're the functions on the other way. The simplest example is polar coordinates. So in polar coordinates, the functions are log r and theta. Those are the harmonic conjugate functions. And the level sets are rays or concentric circles. All right? Now, after thinking about this for a while, I realized that actually I also want linear combinations of these. So when you set that equal to a constant, you're going to get what are called Bernoulli spirals. Right? That's what these things are. And over here you have the analogous thing, some kind of spiral, which is the linear combinations of the two harmonic conjugates. So you sort of interpolate between all of this stuff. So that's what it says down here. A lot of this, you have images of parallel lines under these mappings. And these degenerate case would be just the exponential. And there's one other degenerate case, which is the quadratic function. These you get just by taking limits of this in various places and rescaling. Okay, so this is what it looks like oh yeah, so this one, the last example is the simplest by far. Z goes to z squared. In fact, the level sets are all confocal parabolas. all the way around. When you rotate, you just keep on getting parabolas. It's just that the axis changes. And if you rotate by, what is it? I don't know whether it's 180 degrees or 90. Yeah, 180 degrees. They'll actually be perpendicular to each other. Okay, so that's what they look like. And that's what they look like in this example. So, so I have a whole other slide which tells you what they are in coordinates. In coordinates, so, I used the hyperbolic cosine. I could have used the cosine, right? These are functions of a complex variable. The hyperbolic cosine and the cosine are the same if you're doing complex analysis, right? And I could have used a sine function. That's just a shift. This is just all the same function. Modulo this, I apologize, I will back up to explain. You see, I put in a complex number here and a complex number here. I can also add, I didn't mention that, this rigid motions and dilations, rotations are all involved. So, there's no difference between sine and cosine and hyperbolic sine. So these are all the same thing. Anyway, I wrote down exactly what it is and how you get the ellipse and so on and so forth. And this segment, this is the specific case where the foci are at plus or minus 1. But I don't think we need to really look at this slide too much more. But anyway, it's all there. This is the coordinate system we're talking about. Okay? So now the first question is, what does the coordinate system look like in 3D? Maybe that's not the first question. There's lots of questions even in 2D, but I'm not going to talk about them today right now. Yeah.
So this interval from minus to plus of does that correspond to this collapsed?
Yeah, that's the collapsed thing.
Do you ever consider the limiting the configuration where these 2 points just go to infinity and see what the equipotential surfaces are?
Yeah, so let me just tell you. So suppose you have a segment, and suppose you take one of the foci to infinity. Okay, so one of them is, so now you just have one focus. What you're going to get are parabolas. And that's the example that I just mentioned of z goes to z squared. That's the example of the confocal parabolas. So they're all parabolas, and that slit is the slit of the axis of the parabola starting at its focus and going to infinity. So that's one limit when you do this. And the other limit, which is this polar coordinates limit, you get by taking the collapsing the things together. Okay, so you can do all of these deformations, and this is just okay. All right. I mean, so you can play around with this a lot. Okay. All right. So I'm also going to try to tell you what the word confocal means. So you're familiar with the word focus for ellipses, but you probably haven't really heard the word, and you may be a little uncomfortable with it, and I certainly was when I read it, for an ellipsoid in 3 dimensions. So what in the world is confocal anyway? This is not necessary to understand because they're just a bunch of formulas, but it's nice to explain it. So remember that when you have an ellipse and you take the foci, the thing that's beautiful about them is if you head in a direction and you bounce, right? You're gonna. Did I do this completely wrong here? Yeah. Well, it should have done this. So that means obviously I drew my. Anyway, it's. If you do this, you're supposed to go around in the, if it goes through one focus, it'll go through the other, right? And then it'll alternate foci, right? Now, more generally, if you take an ellipse and you take any trajectory and you bounce it around, it has the following, so this is with equal angle of reflection. It will stay tangent to a confocal ellipse. So the next bounce will be this way. This reflects a conservation law of the billiard flow on an ellipse. Okay? So that's what confocal ellipses do. And now, if you think about it, it turns out that this works in higher dimensions too. if you take an ellipsoid and you take any trajectory, it will stay tangent to a confocal ellipsoid inside. And in the limiting case, you're just going back and forth. And all of those trajectories are just the one dimension down dynamics. Okay, so all that's happening is that you think of your ellipsoid, and then in this slice, there's this flattened ellipse, and the situation of that ellipse is exactly the same as anyway. So this is what confocal means, if you like.
So when you have this three-dimensional ellipsoid, are they rotationally symmetric so that you have something like plate configuration, or can it be arbitrary?
They're arbitrary.
Oh, really?
Yeah, this is a fabulous set of conservation laws. It's just a completely integrable system, and it's absolutely general for all parameters. Yeah, a lot of people, there's lots of things. Also, spherical harmonics, which many of us have learned about, okay? It turns out that it's something exactly analogous to spherical harmonics for arbitrary ellipsoids. This is complete separation of variables occurs, and there's all these polynomial special functions out there which people have forgotten about because they were only studied in the 1800s. They haven't forgotten? Yeah, I think that there are a bunch of engineers who do this. Actually, when I looked it up on the internet, I can't remember. There were people in fluids. There were all kinds of people who were solving PDEs using these expressions. Yeah, not just the shape of the Earth, also submersibles and various other funny things that are going around. Anyway, yeah, but I'm sure that there's, Okay, all right, so let's see. So I explained this slide. So this is just in words what I just said about the trajectories. And now I'm going to move on. I'm not going to, as I say, I'm not really getting where I wanted to go, but I'm introducing you to this idea of the solitons anyway. So remember, in spherical coordinates, the Laplacian splits in this way, in separation of variables. And historically, the reason why people thought about these ellipsoidal coordinates is that there's a splitting, a natural way of analyzing the Laplacian. So here's the more general fact, which you may never have noticed, but is very easy, which is that actually there's a splitting for arbitrary harmonic functions with gradient not zero. So if you take an arbitrary harmonic function with gradient not zero and you use the coordinate, which is the function itself, and then as your other differential operator, so you're going to do differentiation with respect to that variable. The other differential operator is the Laplace-Beltrami operator for the surface. Then it will split completely in this way. Okay, this is a very routine calculation. And this, so wait a minute, this looks simpler than that, you say to yourself. But think about it. It's the fundamental solution. It's r to the 2 minus n, which is the harmonic function in n dimensions. And if you put in r to the 2 minus n, you will get rid of this middle term. And that's all that's going on here. And it turns out that it's general for all harmonic functions. So this is maybe the first very elementary coincidence, which is telling us that we should be thinking of level sets with harmonic functions. Now, the miracle with these harmonic ellipsoidal coordinates is that you get a complete separation, not just in the one direction where u is, but all of these u's. And that's it. The Laplacian is just this. Okay, and this is actually just a trivial consequence of the fact that the gradients are orthogonal to each other. So this is immediate from the perpendicularity. Now, this is not the coordinate system that people study. They did something much fancier than that. Because notice that this is not a complete coordinate expression for the Laplacian, because these gradients are not expressed in terms of the variables u1 through un. If you want to rewrite it as a separation of variables, you also have to understand these coefficients. They're clean in the sense that they're separated, but we still have to understand this gradient.
So the gradient is with respect to which variable?
This is the full gradient of this function. It's a function in all of space, and it's just the length of its gradient. It's just how long it is, so that you compensate the d by du squared.
So the gradient is the coordinates here that you're talking about is u1 up to un, and now you're taking the gradient of u1?
Correct.
Well, wouldn't that be simply 1?
So
U1, the gradient of u1, so
yeah.
you're taking the partials with respect to
I'm taking the partials with respect to x1, so the Laplacian is d squared dx1 squared. Sorry.
all these original, all of those guys.
Okay, and then you have these functions, and now you're changing variables to these functions. And the gradient is just the ordinary gradient. Laplacian is the ordinary Laplacian, and now we're changing variables. Okay? And if you take a bunch of variables and they happen to be perpendicular to each other, then this would be the correct way to write the Laplacian. As it happens, because of this separation here. That's correct. Okay? Because there are no first order terms. So it's okay. All right. So now, but as I said, I'm not done yet, because I haven't explained to you how to rewrite these in terms of the coordinates u1 through un. Okay? So here's the formula. It's very famous in 3D. It was something that was written down by Jacobi first, and they're called elliptic functions. And Jacobi invented them around 1840. And they look practically like sine and cosine. Okay? They're ratios of theta functions, which he also invented at the same time. And they are related to uniformization and a lot of algebraic geometry. And what they are is they're these functions sin, kn, and dn, which I'm abbreviating by capital S, capital C, and capital D. Anyway, but this is what you'll read in the literature about them, is these abbreviations here, these things, which are sort of, the SN and the CN are sort of like sine and cosine, and then there's another one because it's not circular functions, it's functions in three variables. And what you do is you take initial conditions, S of 0, 0, C of 0, and D of 0 are both equal to 1. Okay? And then you solve this system of equations. It's just an explicit system, first order system of ODEs. And you need one initial condition, right? Nonlinear ODEs. Okay? And there is one parameter, and the parameter comes from the ellipsoidal constants that were involved. Okay? And this thing has a name, but I've forgotten what it's called. It's called the elliptic something, or I don't know. Ratio, I can't remember. It's got a name. Okay, and now here is the coordinate formula. All right? The coordinate formula is you just take products of the sums, the sums here, okay? Now so it's a very, very simple formula. And then there's a beautiful formula for the metric itself, which is also completely explicit. So this is what actually gives you the Laplace-Beltrami operator in terms of the correct coordinate systems. It's just sort of the most symmetric thing you could possibly write down in terms of these functions.
Might be important to introduce elliptic with the presentation.
Hmm?
For what purpose did we introduce it?
So I don't actually know. the question is, why did he introduce this? And I don't know the history of why he introduced this. So the theta function is actually just the solution to the heat equation on the circle. And it has some symmetries. It's periodic, and then you extend it to a complex variable, and then it has another quasi-periodicity. And these things are ratios of those functions. So they have periodic poles, and there's some kind of meromorphic function. And it's related to uniformization. So one possible reason why he might have done this is that he was interested. So here's a possibility. So you remember this function here? Okay. So this is the first function that's not a polynomial, right? It's the function. Well, yeah. It's this function. Okay. But now in the 1800s, they understood complex variables. And this function bothered them tremendously because it's multi-valued. Okay? So maybe it's a better idea to consider the function which is the inverse function of this. And that turns out to be an entire function. Okay? And then you study the periodicity of this, which is very interesting, and you get the full understanding of what the logarithm does. So what this is the same thing. So if you then also try to integrate functions like this, where you have a quadratic in here, then you get, an example would be this function here, right? Which would be the sine function. Or, sorry, the arc sine function, which is horrible because it's multi-valued or sort of weird, but the sine function, the inverse, is great and has its periodicity properties. Okay? So this is what you do when instead of you have a quadratic here, you have a cubic. And if you're trying to analyze what's going on and you have to think of complex variables, you think, oh, maybe I should use the inverse function. And so he cooked it up. He did it. So I mean, that's a guess. I'm guessing. That may be why he did it. Yeah. Well, so it's probably very directly related to, so first of all, Schwartz is, I think, a little later than Jacobi, but so it certainly is related to various kinds of tilings and conformal mappings. And in fact, this is used in uniformization. So the second person to study this, by the way, was Weierstrass, who solved the problem in higher dimensions for the hyperelliptic integrals, it's also related to something called abelian, the Jacobian, which is some kind of, anyway, so what this has to do with is covering spaces by periodic things. So this is the coordinatization of elliptic curves. So it comes up in number theory. And Weierstrass's parametrization is in terms of the Weierstrass P function, which is just another way of rewriting these functions. But then the P function has these, it makes it a little easier to write down what's happening for when you move from quadratic to cubic to general degree polynomials, which is much, much more complicated.
So when you took the logarithm of the first kind of polynomial, that's because it was the simplest.
Yeah, I'm calling it the first. I don't know. It's also, of course, the logarithm is the first function that was invented that was a transcendental function, long before the exponential was discovered.
Right. Okay. And then you went from linear to quadratic to cubic.
Right. I mean, I'm sorry. This is not historical. This is just me making up a guess as to what it is. I honestly haven't looked at this question.
And it goes without saying that the gamma 1 there is an expression which is 1 in the numerator and all the rest in the denominator.
Yeah, this should be this is a product. All of it is in the denominator. That I should have put parentheses around this so that it would be unambiguous. So let me just make one more comment about this slide, which is going to make you very uncomfortable. You see this I here? So this is a formula in several complex variables. This is not a formula in real variables. And the signature of these quadratic forms is a little ambiguous, and you have to make sure you have to watch out when you, it's very, very important to take out the square roots, because then maybe you would have branches. There's all kinds of problems in this subject you have to be very careful and precise about. So, unfortunately, when I square this, that doesn't mean that it's positive, because, and it's on the previous page. Oh, no, the one before that. Yeah, here, way, way back. So notice that this number is not, this denominator, which we're taking the square root of, is not necessarily positive. So some of these numbers are imaginary, pure imaginary, not okay. So, so you have to be very careful about what it is that you mean by these formulas. Well, we're almost out of time, and I'm going to just tell you what the goal is, and we're going to have to discuss the rest of it next time. So here's the goal. You start with this function, which is harmonic. Its gradient is not zero, and what we're trying to do is to find all of the geometric invariants of the level surfaces, which are zero in the model case, in the soliton case. This is what Hamilton wanted us to do in his context, and that's what we're going to try to do in our context. So we have these guys, these UJs, these very weird functions, which I just described to you, all right? And I want them, and actually even more, I want the spirals, not just the theta and log r, but I also want the linear combinations of them to be such that, so whenever I take one of these functions and I take any rigid motion of these things and I take any combination of them, I want to be able to use the Taylor series so that, sorry. I just want to find all these geometric invariants. And as a special case, what has to happen is I'll have to be able to know if I land in a certain part and I take the Taylor series, I need to know exactly which of these functions I've got. Okay? And it's going to turn out that in order to do this properly, we need 3 derivatives of the function. And then eventually, in order to write down all of the invariants, at least 7 derivatives. Okay, so it's going to be a little complicated, and in order to keep track of those, in order to understand what could possibly be going on and not lose your place in formulas which are actually, dozens of pages long, you must use invariant notation, differential geometric tools. Otherwise, you're never going to be able to write closed formulas that make any sense. So we have to write this in a coordinate invariant way, and in order to do this, we're going to talk about ordinary classical Riemannian geometry, extrinsic geometry of hypersurfaces. And then it turns out that it's very relevant to what's called affine geometry, in which the natural objects, instead of maybe spheres are constant curvature things, are ellipsoids. And then we're going to create an analogous geometry, which is our geometry, which is going to, I claim, I hope, get all the way through to the end of this subject, which I'm only, partway through, but I have concrete formulas, which I will show you next time. So we're stopping a little early, but people kept on asking questions, which is very helpful. That way you actually understand what I'm doing,
so
maybe.
Tomorrow,
Yeah.
going to then come back also to the second fundamental form, the extrinsic curvature, and see how that goes.
Yeah, I'm going to start with the first and second fundamental forms.
Yeah.
And then I'm going to create something and then I'll explain the affine first and second fundamental forms, which are completely different, but are based on similar ideas that go back to Blaschke, having to do with affine geometry. So it's invariance under SLN and GLN instead of the orthogonal group. And so we have to explain that. And then once we have those models, we'll be able to do my geometry, which is I'm calling harmonic geometry, and it will be analogous to those two. And then it will just unfold, and we will get a first, a second, and a third fundamental form. And we'll see. Okay? So that's what we're going to do.
So what would this actually give you to know that there are no series?
So what would this give you? So you of course, you could always write down the Taylor series. You have to write down coherent tensors which are built out of the Taylor series. And then what you want is a differential inequality. You want to be able to take the Laplacian of something and get a maximum principle. And that maximum principle will then allow you to deduce pinching theorems and Harnack principles and monotonicity formulas.
So use this expansion, Taylor expansion by these solitons, apply them to get some.
You use the solitons to see what formulas could possibly be the right formulas that will cleanly be equalities for the solitons, and then there'll be inequalities for in the general case. But inequalities with a favorable sign so that you can actually prove theorems using them.
So if I understand it, so Hamilton and the other consider movement by the unique arbiter. You want to know what kind of other movements will lead you to something theorem.
What Hamilton did is he studied motion by mean curvature, and then the question is, where does the flow go? What does it do? And the first pinching theorem says if you start with something which is convex, what will happen is it will get smaller and smaller and smaller, no surprise there, okay? But it will get rounder and rounder and rounder. And it will actually vanish at a single point. It will encounter a singularity, and there's a complete characterization of what that looks like. It'll get closer and closer to a sphere. That's the pinching. And then it will just go. And that's the analysis of that is that essentially there's only one ancient solution. There's only one convex solution, which is, so if you rescale, it's ancient. It means it goes from time minus infinity to 0. And it comes along, and there's only one. It's just the shrinking sphere. And so that's what you want to prove. That's the type of thing you want to prove. Or that Hamilton proved, I should say.
So you want to do this with different kinds of motions, is that it, or what?
I want to do it for level sets of harmonic functions and eigenfunctions. And I want to be able to get information about how the different levels talk to each other. Which is what he's doing. He's doing different levels of the mean curvature. It gets better and better and better, and then it does something. And I'm saying, for instance, in the case of the ground state eigenfunction, it gets better and better and better, and also it kicks in. It's already good by the time you're halfway up, or something like that. That's the. Yeah, that's the type of question for which that's the pinching. The statement is that basically you're almost nearly the same ellipsoid once you're halfway up. You're already the same sphere once you're halfway in. From an arbitrary convex body, once you're halfway in, you're practically round, and you're getting more and more that way.
In 2 dimensions, you don't have to start with a convex domain. To do the
Yeah. So if you drop convexity, then you're going to have to. So that's like trying to do what Perelman did, which is starting with arbitrary manifolds. And then, so of course, there could be, it could be the real jackpot, which is that you don't just prove these special theorems with this particular geometry. You have something very, very general. But then you have to do, presumably, surgery and so on. So that's what I, was trying to say last time with the triangle. You have the 3 things, and then you have this neck. So this is the surgery. So the singularities, the places where the gradient vanishes, are Perelman's singularities, which is something that Hamilton could not handle, but Perelman could. Is what happens at the singularities.
the Arnold Ross summer program.
Yeah.
Arnold, you were mentioning what he was saying, namely, think deeply about simple things.
Yeah.
At the time, you probably did not appreciate that because your context maybe was not as big as it is now.
Extremely
Looking
limited.
back on all this time, where in your thinking development did you find useful or resort to Arnold Ross's thing where he said, think deeply about simple things? Were there in the past X number of years, were there things where you said, oh, okay, now this is fundamental, this is simple, and so I'm now going to zero in on this, and if you do this on fundamental things, which are universal, then chances are that there's a good payoff here on this.
Well, I'm very hopeful that I'm onto something like this now, but I can't pretend that I was ever able to reach that level of in the past.
I don't know. Since he's here also, yes, tomorrow, and the office number is 510. So you can discuss it.
I see.
Yeah.
Okay.
All right. Anyway, thanks.
Because I think you probably want to talk more in more detail. So I'm not stopping the question, I'm stopping the answer. So thank you again for the second time.